Привет. Yeah, yes. That's the only Russian I know except for this emoji that has a character in it. So please come teach me some Russian. I don't know any, and I would love to learn. My name is Aaron Patterson. I'm also known on the internet as Tenderlove. That is my nickname. If you don't recognize me here on stage, this is what my picture is online. So we look a little different, but that's really me. So, I work for a tiny startup called GitHub. You may have heard of it. It is the very first legit company I've ever worked for. I really love using Git, but I will not force push it on you. Okay, actually, let's see. 1 second here. This is not, there we go. Okay. So I will not force push this on you. Now, I know like I've been using a lot of Git puns lately since I work for GitHub, and I think that these puns will have opened a lot of, like, they have allowed me to branch out. They've opened a lot of doors for me. Now, did I say doors? I actually meant windows. Sorry. All right, yes. So I have two cats, and they are very adorable. I love them so much. This one's Gorbachev Puff Puff Thunderhorse, and my other cat, her name is SeaTech Airport Facebook YouTube, and I have. We named her that because she has no idea what her name is, so it doesn't matter. Anyway, I have stickers of my cat, so if you want to come say hello to me, just come say hi, and I will give you a sticker if you just ask for it. I want to say thank you so much for having me here. Like, it's really, really an honor for me to be here in Russia, meeting all of you. I'm really happy to be here. It's really an honor. I was actually here 4 years ago, and it was really, really great. I got a 10-year visa. Like, it was a really, really good visa. 10-year visa. I could come back to Russia as often as I wanted to and stay here for 90 days. And unfortunately, I lost my passport. So I had to get a new visa, and this one was only a 3-day visa. So yeah, I'll have to come back again and get a better one. But anyway, I am going to talk to you today about reducing memory usage in Ruby. We're going to talk about two optimizations that I've made in Ruby 2.6, and I'm really excited. This is really great. On the first talk of the day, it's 10:14 a.m. and this is going to be a hardcore technical presentation. So I apologize, but you'll have to bear with me here. We're going to talk about two patches today. Essentially two different stories, but I'm actually really excited to tell these stories here in Russia because one of them has to do with a Russian programmer that I don't know if he's famous here, but he's famous to me. I enjoy his work a lot, so it's exciting that I can talk about him a little bit today. But anyway, the first story we're going to look at is loaded features cache. We're going to talk about loaded features cache, patches to improve that, and then we're going to talk about another one that I call direct instruction sequence marking, which we'll talk about that. But these are primarily geared towards these patches are geared towards reducing memory usage in Ruby. But in order to reduce memory usage in Ruby, we first have to find memory usage. So I'm going to talk about that a little bit. Now, Ruby is written in C, so I'm going to talk about finding memory issues written in C-based programs. And there are two ways that I use to find memory issues in C. And the first technique that I use is a very bad technique. I don't like this technique at all. But the very first technique that I use is called reading the code. I read the code, and and then I see, oh, we use a lot of memory here. But I would prefer not to use this technique. However, sometimes I need to. The other technique that I use is called Malloc stack tracing, And in general, this is a more general way to use Malloc. In Ruby, we have to worry about two different types of allocations when we're working with our programs. We have two different spaces where memory can be allocated. One, we have to worry about memory allocations from the garbage collector. And then the other one we have to worry about is allocations that come from Malloc when we ask the system for memory. Now, when we want to profile any sort of memory usage with the garbage collector, we actually have a lot of tools for that already, including object space. We can use methods on the object space module, as well as the allocation tracer gem. But these gems only give you information about objects that are allocated inside of the garbage collector. They don't really tell you much about what's going on with the system allocator, or Malloc. So we have good visibility into the GC, but we don't have very good visibility into Malloc. So to find our Malloc-based allocations, I like to use a technique called Malloc stack logging. And this tool is available on OS X. We're going to talk about one that's specifically available on OS X, but this type of tool is also available on Linux as well. Just the commands that you use will be a little bit different. So we'll look at OS X, but you can apply the same things on Linux. So the way we use this on OS X, this is what Malloc stack logging looks like. First, you just need to enable the logger by setting an environment variable. This particular example is where I'm going to be profiling the boot of a simple Rails application. So first we enable the logger. I'm setting the Rails env to production because we want to test in the production environment. Then I have a small program that just prints out the PID, then starts the GC, and then just sleeps. And we have to profile live, with this technique we have to profile live programs because of address randomization. So we have to look at it while it's alive. So I basically put the program to sleep. Then in a different terminal, I'll use this program called Malloc history, where I pointed at a particular PID, and it logs all of the mallocs and frees that your program has made. So this will print out every single malloc and free that your program has done, and then I redirect it to a log file. Now, when you use this technique, it is very, very important to have a lot of free space on your disk drive, because this is profiling a very basic Rails application. It's not our production application or anything like that. It's just a basic Rails app, and the log file is 6.2 gigabytes. So you need to have some free space. But anyway, if you look at this file, the file contents look a bit like this. It's just got each line shows you an allocation or a free. So in this particular example, we have an allocation, and that allocation is at the address 0x7fb, whatever. And then later on, we have a corresponding free, or not a corresponding free. This is just a free. So you can see what addresses were allocated and what addresses were freed. And if you combine all those together, you can figure out what memory is available, or what memory has been used and what memory has not been used. So we can actually reconcile that live memory using this Ruby program. You don't need to read it so much. Just know that it takes all those allocations and subtracts the frees in order to calculate how much memory we're actually using. So what's cool about this is that we can know how much memory the program is using at any point in time. So all the way from the very beginning of the boot of the process, all the way until we pause it, we know how much memory the program is using at any point. Then we can also know how much memory the program is using while it's paused. So we can figure out exactly how much memory we're allocating and who is allocating it. But a good question is, who calls Malloc? When we look at those stack traces, we see the very top of it is Malloc, and we don't really care that somebody called Malloc. We want to know who called that. So if we modify that program a little bit, we can just look at the caller of Malloc. And then if we look at the caller of Malloc, we can figure out who is allocating memory. So here's an example. Taking that heap dump, I broke out all the callers of Malloc, and you can get a breakdown of who is actually allocating memory in MRI. Now, you don't need to read these necessarily. It just shows you where you should start focusing your efforts. So we'll look at the biggest slice, and we'll start focusing our efforts for reducing memory there. So to reduce memory there, I combine the two techniques. I combine these two techniques. First, I instrument it, and then I read the code. So I figure out where that allocation is happening, then go look at that function and see if we can reduce the memory. So now that we know how to find where we're allocating memory, let's take a look at this loaded features cache. Now, to talk about this optimization, first I want to talk about something called a shared string optimization. Shared string optimization is where we have one string buffer and multiple objects that are sharing that particular string buffer. So here's a simple example. We have x, a, and b. X points at this string buffer, and then a, when we duplicate it, it becomes another Ruby object, but it's just pointing at the head of the same string buffer. And then B, when we take a slice from A, it goes from that letter A all the way to the end of the string. So all three of these Ruby objects can share the same underlying string buffer. Now, unfortunately, what this means, the way that this string sharing technique works, it means that we always have to slice all the way to the end of the string in order to get this optimization to work. So let's take a look at a non-shared string. So for example, we have this variable x. It's pointing at the beginning of the string, and we have a variable a, which only takes the first two characters. Now all these strings have to be null terminated, and since we can't null terminate there, we have to actually allocate a new buffer for that. So we'll have to actually allocate a new string buffer for a. So we have two string buffers. So our shared string rule is always copy to the end if you can, okay? This way the string buffers can share the underlying memory, and we're going to use this optimization to reduce the loaded features cache memory usage. So loaded features, what is this? The loaded features is a global array. You can take a look at it when you're using your Ruby programs like this. It just keeps track of every single file that has ever been required. So if we take a copy of the array before foo, we require foo, and then look at the difference afterwards, we can see what file we required. Now, we have to be we can require the same file over and over again, but Ruby knows to only load that file once. So if we execute this program, foo only gets required once. And Ruby uses the loaded features array as sort of a database to know what has been required and what hasn't been required. So Ruby has to figure out, okay, when you load this file, is this file that you just tried to load, is it the same file that's in the loaded features cache? So that gives us a question like, what is the same file? What does that mean? So this is actually a kind of complex problem. Here's an example. These all require exactly the same file. So even though we're changing the load path and requiring some string, all these requires load exactly the same file, but we expect that file to only be loaded once, even though we've passed all these weird parameters to require. Now, Ruby, when we have to look through that database, we don't want to look through the array because an array search is slow. So looking through that array would take forever if we're trying to boot up Rails and look at all the files that we required. So in order to make that fast, Ruby actually keeps a cache of indexes into the array. So this cache consists of all the parameters that you could possibly send to require. So for example, when we require this file abc.rb, the cache gets created. Now, if the same file is required again, there's a fast way to determine whether or not that file has been seen. So this cache on the right-hand side gets generated as soon as we require that file. Now, if you require any of those files, Ruby will know, let's take a look at this one and see if they're the same. Now, the cache structure looks something like this. It's basically just a hash with every possible combination of require on the key and then the index into the array as the value. That way, when the file gets required, we can check the loaded features array and see if they're in fact the same file. So let's take a look at the generation algorithm. This is a translation of the cache generation algorithm in Ruby. It's not actually this. This is written in Ruby. The real one is written in C, but I've converted it to Ruby because this is a Ruby conference. Not a C conference. So it's a little easier to read, but we're not going to read it because it's actually still kind of hard to read. I made some diagrams. So this is what the key generation looks like. If you require abc.rb, what happens is Ruby takes, it starts out with 2 pointers at the end of the string, and then it first moves 1 pointer back to the first period, then moves the second pointer back to the first slash, and this gives us the first 2 keys in our hash. So we get c.rb and c. Then we move backwards again. This gives us the next 2 keys, then we move backwards again. This gives us the next 2 keys, and then we move all the way to the end of the string, and then we have the rest of our keys. So we're able to move these pointers backwards, calculating to the end of the string and figuring out all the keys for this particular hash. Now, if we take a look at the way that these are actually generated, Ruby is taking a substring of each of these. So when we look at the Ruby objects that are generated with this, we call RB substring on all of these to generate the string key value. And this actually creates a new Ruby object for each of these keys. Now, unfortunately, this means we end up with 8 Ruby objects. And because we weren't slicing all the way to the end of it, we end up with 4 different string buffers there. So we end up with 8 Ruby objects and 4 calls to malloc in order to copy these strings. So we can actually reduce these mallocs by using this shared string optimization we talked about earlier. So in order to do that, what we do is we first take a copy of this key. We start out with the original buffer, we copy it to the right before the .rb, and then we take substrings of those. That way, when we do RB substring on each of these, we end up with just 2 buffers total. So we'll end up with the same 8 Ruby objects, but they all point at just 2 different string buffers. Now we can actually eliminate these Ruby objects as well. So we can do one more optimization. If we look at the loaded features cache, it looks like this. We have this hash that points at a whole bunch of Ruby objects, string objects, and each of those Ruby string objects points at a string buffer. But this hash is actually written in C. It's not a Ruby hash. It's just a C hash. And what that means is we don't actually need to have Ruby objects for the keys. We can just point directly at the string buffer. So instead of the hash pointing at Ruby objects, we can make the hash point at those buffers exactly. So we do this and just point straight at the string buffer, and that's able to represent all the same data. So I wrote a patch that did this, and this is what the implementation looks like. And you can see it is very easy to read. That is it. So I applied this patch, and then we measure the impact of this patch. Now, the way that we measured this, or the way I measured this, is I said, okay, I'm going to use the allocation tracer gem. I'll require a very long file name, and then calculate how many objects we had to generate in order to require this particular file. Now, the output of this, it looks like this. On Ruby 2.5 is the left side, 2.6 is the right side. This is hard to read, so I made a graph. If we compare the 2 graphs, this is what it looks like. So we're able to cut the string allocations in half on Ruby 2.6. Now, this just looks at the Ruby objects that are allocated. We also need to look at the amount of memory that we malloced, and we use that with Malloc, our Malloc stack logging again. And this is a graph of what the Rails boot process looks like over time. So the red line is Ruby 2.6, and the blue line is Ruby 2. Or the red line is 2.5, the blue line is Ruby 2.6. So we can see before we allocated more memory and called malloc more times, and after we allocated less memory and called malloc fewer times. This actually turns out to be a savings of 4.2%. So with this patch, you save 4.2% on a regular, just a plain old Rails application. Now what's interesting about this is the amount of memory you save depends on the amount of code that you load. In other words, the more you load, the more you save. How much would you pay for this feature? 100 rubles, 1,000 rubles, 1 million rubles? Today, you can have it for free. Just by upgrading to Ruby 2.6. Yay! So I can't tell you how much memory this will save because it depends on your application. But like I said, the more files that you require generally, the more memory you're going to save. Now I have a little story about this patch. I submitted this patch here. This is the URL. I was really happy about this. I measured everything. It was looking very good, so I sent the patch. And then I got a comment on it by Funny Falcon. You may know him. He said to me, "Okay, did you compare it to this other patch?" And I didn't know about this other patch, so I was like, "Oh no, I better do that." So I went and looked at the URL. I looked at that patch, and it was this lightweight structure for loaded features index, and his patch was almost exactly the same as mine. It was very, very close. Like basically the same, he solved exactly the same problem I did. Now, unfortunately, when I looked a little bit closer at this patch, I saw that he had submitted this about 5 years ago. So I applied his patch instead of mine because I think he got there first. Anyway, the point is always search the issues. So the next thing I'm going to talk about is direct instruction sequence marking. Unfortunately, this technique means that we need to know a bit about how Ruby's VM works. So I'm going to talk about Ruby's VM. Ruby's virtual machine is a stack-based virtual machine, and what this means is we have a list of instructions in a stack. On the left are our instructions, and on the right represents our program. The instructions represent our program, and the stack contains the results of our program. Our instructions have a name and 0 or more operands. So we also have a program counter that always points at the next instruction that we're going to execute. So if we look at the way that this program executes, so there's our instruction, there's our operand, there's our program counter. It's always pointing at the next thing we're going to execute. So the way this works is it says, okay, we're going to push the number 3 onto the stack, then we'll push the number 5 onto the stack, and then finally we'll add those 2 numbers and push the result onto the stack. So we end up with the number 8. But how do we get these instructions? Like, where do they come from? We know how the virtual machine works, but where do we get these? So the way we get these is by compiling our Ruby code down. Ruby compiles all of our Ruby code before it executes it. And our Ruby program, actually every run, it has to go through a few phases. And the processing phases we have to do are taking our source code, which is text, converting that into an AST, then we convert the AST into a linked list, and then we convert the linked list into some bytecode. We'll look at how these things work more in depth a little bit later, but I roughly divide these into 2 different steps, which is our parsing and compiling phases. And they get kind of gray and fuzzy, but that's kind of how I think about them. So optimizations to our code are actually applied during the linked list phase, and the reason is because linked lists are easier to manipulate than trees. And our final product is the bytecode. That's what we want to come up with, and that's what we're going to be executing. So the data structures that are involved, the first thing we need to do is convert to an AST. We have an abstract syntax tree, and this is just a fancy way of saying a tree data structure. It's a tree data structure that represents the syntax of the program that we're parsing. I'm not sure why it's called abstract, because it's concrete when we end up with it, but this is the name, so there we go. So our parser converts this text, which is our Ruby program, into an AST. First we have a node that represents the operator plus, and then 2 nodes that represent the numbers 3 and 5. And what's cool about this is that if you read through the C source code, these nodes are actually Ruby objects. They are Ruby objects. You just never see them in your Ruby program. They're T-node objects. Now we take that AST and we have to convert it into a linked list, and the way we do that is through a recursive visitor function. So first we'll visit the plus node, and then we know that the plus node has children, so we have to visit the child first. The number 3 does not have any children, so we add a node to the linked list, which is push 3. Then we add the other child, 5, so we add a push 5. And then we are done visiting all the children, so we go back to the parent and we add a plus node, which is just our add instruction. This is a doubly linked list. Now, when we build the linked list, the code looks a little bit like this. Of course, it's all written in C. This is a very simplified Ruby version, but this is essentially what it looks like. So we walk all the children before we apply the parent. Next, we apply any optimizations. And I am going to do some hand waving over the optimizations because there are a whole bunch of optimizations, and we don't really need to care about them today. So after we apply our optimization pass, first we have our linked list. Our linked list gets optimized into exactly the same thing. This is our optimized linked list because we're not optimizing anything today. It's a different topic. And then we have to convert it into bytecode. But what is bytecode? Bytecode is just binary code executed by the virtual machine. And if you look at this bytecode, it's literally just a list of integers. That's all it is. It is just a giant list of integers. That's it. So the way we get this list of integers is we take this linked list and we have to translate the linked list into bytecode. In this case, we might represent the push instruction. We'll translate that first node. We'll represent the push instruction as the number 1, 2, 3, just for example. And then we'll add the number 3. And then we'll have another 1, 2, 3 for the push instruction, and then a 5. And then we'll add another instruction for add, which we'll just say is 4, 5, 6. Oh God, 10 minutes. Let's move. All right. I'm never going to get done in time. I'm sorry. Anyway, so we end up with this bytecode. This bytecode is stored on, remember these are all Ruby objects. We end up with some bytecode which is stored again on a Ruby object. This is an IMMO object. And now we'll make a simple VM for executing this. So just to refresh, we have a stack-based virtual machine. We need to keep track of a program counter. Now our program counter has to iterate through each of these numbers. So you'll notice that we don't go 1 at a time. We actually go 2, and then 2, and then 1. Our PC increments by 2 to 1. So we'll create a simple virtual machine. This is our simple virtual machine. We are pressed for time, so I will not read it to you. But we have to increment 1 extra in the case of a push. In the other case, we just increment by only 1. So we know how compilation works. We know how the virtual machine works. And this is a really good accomplishment for us, I think. Now we're going to do one more. We're going to compile one more program that's very similar. But this program does not use mathematics. This program uses strings. I think a lot of us deal mostly in strings when we're working in the web, so this is important. So we have a case here. We have 2 strings, and we do exactly the same thing as we did in our math example, except that we use puts. We have that chevron, and then we say hello and world. Now, when we compile this AST, those strings are actually represented as Ruby objects. They're truly Ruby objects. They're just Ruby strings. Now, we convert the AST into a linked list again, going through exactly the same process. And those operands there, those are the same Ruby objects. They're exactly the same Ruby objects. They're just copied over there. Now, when we convert this linked list into bytecode, we go through and translate each of the nodes just as we did in the mathematics case. But here, we have to embed these Ruby objects. Now, the bytecode is only integers. It can't actually hold objects, so we put the address of the object in there. Those are actually object addresses, not the actual Ruby objects, but it's the address of that Ruby object. It's pointing at that Ruby object. So now we have our bytecode. And we're going to write a VM again in Ruby, but in Ruby, obviously, we don't have pointers, so I'm just going to embed the strings themselves. So this is the bytecode that we'll use. The actual bytecode will only have integers in MRI. So our VM implementation, again, it looks like this. It is hard to read. If we run the VM, this is exactly the same VM we used with the mathematics process. Here we're going to run the VM twice. And if we run it, we'll see that we have a bug. It prints out hello world, then hello world world. So we have this bug. Why do we have this bug? The reason we have this bug is because we have 2 Ruby objects in our instruction sequences. And when we increment these, when we walk through this, we'll see that we push that Ruby object onto the stack, push another Ruby object onto the stack, and then we append it, and that actually destroys the other object. Oops, I messed that up. Anyway, so we are actually embedding those Ruby objects into the stack there, and it actually mutates them, so we end up with hello world, a hello world object there. So we can't do that. That's bad. We don't want to do this. So the way that we deal with this, and then when we execute the program again, we get exactly the same problem, except that we end up with hello world world, and et cetera, et cetera. So if we execute this program 3 times, we get a whole bunch of worlds, and that's too much world. We only need 1 world. So our new VM, what our new VM does is it just copies that object and puts it onto the stack. So when we execute this again, if we dupe it, we see that we have these copies on the stack, and then we don't mutate the original one, and everything works fine. So if we count the number of objects that are allocated when we execute this program, we have 3 objects that are allocated at compile time, and then 2 more objects that are allocated at runtime. Oh my God, 5 minutes. Let's do this. So side note, this is why frozen string literals save us so much memory. If they're frozen, we know that we don't have to duplicate this object when we put it onto the stack. So now that we understand the VM implementation, we know why this frozen string optimization is helpful for us. And I just think that's neat. So reducing memory usage, I think we talked about the VM enough, so we'll talk about how this technique works. So bytecode is stored on instruction sequences, instruction sequence objects. Instruction sequence objects are just Ruby objects. That means that these are managed by the garbage collector. Now, just a side note, when I say iSeq, that just means the same thing as instruction sequence. And if we look at our iSeq layout, it refers to some bytecode. It has a list of bytecode here. And remember, these bytecodes are just integers, and these integers point at the address of some Ruby objects. So in these cases, hello and world. But we have to make sure that those objects don't go away. If they get garbage collected, then when we execute our program, everything is going to blow up. So we have to make sure that those strings don't get GC'd. In order to do that, we have a thing called a mark array. And this mark array just keeps track of all the Ruby objects in the instruction sequence. So our mark array, when we compile the program, all of these strings just get added to the mark array. Go transitions, yes. So we add hello, hello gets added to the mark array. We add world, world gets added to the mark array. But the instruction sequences also point at those Ruby objects. So when the garbage collector marks, it marks the instruction sequence object, then it marks the mark array, and then it marks all of these objects that are inside the mark array. Now, a problem with the mark array is that we have an organizational problem. We have multiple references to these Ruby objects when really we only need one. We have duplicate information here. I'm going to move quickly. We have hidden references. These references exist, but if you just read the code, it's hard to know that they're actually there. We also have a problem of array bloat, where an array can store more elements than are actually inside of it. So if we look at an array and how it grows, you can see that blue line is the number of objects in the array, and the green line is the amount of data the array can actually store. So all of this data that's unused in between here, we can think of that as bloat. It's unused space. Now this unused space also occurs inside of this array, and this array lives forever. So we have this unused space that's sitting around in our program. So how can we remove this bloat? We can remove the bloat by shrinking the arrays, but what about just removing the arrays themselves? So we can remove those arrays. The way that we do that is just by decoding these instruction sequences and then marking the objects through decoding them. So if we had a function that can decode the instructions, then we can mark those objects. Now this code looks exactly like our virtual machine looks, except that instead of executing something, we just mark it. So rather than executing it or pushing onto the stack, we mark. So practically speaking, this means we can eliminate the mark array because the instruction sequences can just mark it themselves. So this is what I say is we're marking these objects directly, and why I called it a direct marking technique. So in the real world, let's look at how this impacts us in the real world. We have an array reduction there. You can see T-array there in Ruby 2.5. Ruby 2.5 is blue, Ruby 2.6 is green, and we were able to reduce the number of arrays there. A normal Rails boot, we create 35,000 arrays in Ruby 2.5. In Ruby 2.6, it's only 8.5 thousand. So this is a 34% reduction in objects, total objects at boot time. And if we look at the amount of memory that we're actually saving, that green line there is Ruby 2.6, and I believe the red line is Ruby 2.5. So before, we allocate more, and over here we allocate less. So again, the more you load, the more you save. Woo! How much would you pay for this feature? No, I'm just kidding. So today, you can have it for free by upgrading to Ruby 2.6. Anyway, so I think I'm probably out of time. We have the direct instruction sequence marking code is here. Here's a link to it. Here's the actual code. It's not bad at all. Just kidding. It's pretty bad. It's a long patch. Anyway, conclusion. We learned about virtual machines, we learned about memory management, and we also learned about ourselves. Everybody please upgrade to Ruby 2.6. Thank you. Please come say hi to me later. I have stickers and I would like to meet all of you. Thank you.
Ребят, поднимайте руки, у кого есть вопросы, обязательно задавайте.
Hey, Aaron, big fan of your Instagram, but just wanted to ask, when you talked about the first optimization you did, for someone who is not familiar with the Ruby internals, the obvious solution would be to kind of get the canonical path of the file and then hash it with, to get some integer. So I wonder what are the cons of this method? So why can't we use this?
Let me make sure I understand the question. So the question is, why couldn't we just hash the file name?
Well, I can elaborate.
Okay.
So basically the problem we're trying to solve is we want to know whether the file was loaded or not.
Yep.
And what we can do is we can get the full path to the file.
Yep.
And then apply some hash function and get some integer. And then we can check whenever we want to require, we check that integer with the one that's stored. So why can't we use that?
Yeah, that makes sense. We could do that, but the reason we have this hash, or the reason we have this hash is because the key to the hash is actually the value that you pass to require. So we could do that technique, it's just that it means that you would have to take that string and then calculate the full path.
Yep.
If we have that hash, then we can bypass the full path calculation. So we don't have to do that work.
So basically the explanation is we want to avoid extra calculation in runtime.
Yes, exactly. Exactly.
Cool. Thank you.
Yep.
Еще вопросы, ребят? Нету?
Questions?
Вот, всё.
Yes.
Aaron, thank you for the presentation. Do you already have some plans for Ruby 2.7?
Yeah, I do. So the question was, do I have some plans for Ruby 2.7? I do. I'm trying to finish my compacting garbage collector. I have a compacting GC that I've been working on as I can, and my plans for Ruby 2.7 are to finish that and put it in. Actually, I made a lot of good progress on it, and if you come talk to me later, I can show you some graphs. So it's looking good. But yeah, that's my goals for Ruby 2.7. And then on top of that, I want to do I want to try implementing a variable width allocator. So right now, today, Ruby's objects are only one width, they're 40 bytes. But one advantage that the JVM has over us is that they can allocate they can allocate objects that are any width practically, and we can't do that. So I want to be able to do that. That's one of my dreams. I don't think that'll ever go to Ruby 2.7 though. I don't have enough time.
Еще вопросы? Не стесняйтесь, тяните руки выше. Все. Отлично. Давайте еще раз поблагодарим.